Okay, so then we are back. So now we are in the context of discussing theorem 3311 that states that if you have a family of random variables that has moments that converges to these moments right here that satisfy a growth condition, then we know that the family is weakly convergent. So that is theorem 3311. And we have this lemma from which we know we'll prove this result, and then the agenda is then finally to prove lemma 3, which is the key result, that the moments satisfy this growth condition uniquely determines the distribution. So then proof of theorem 3311. So since by lemma 1 the family is tight, there is a convergence subsequence, say x and k. So we have that x and k converge weakly to x, and so random variable x. So we have weak convergence since the family is tight. Moreover, by lemma 2, the random variable x as the moments mu I. Okay. So here, indeed, we have this. If I look at now the limit as n goes to infinity of the expected value of x n to the I, that is equal to the limit as n goes to infinity of u I n, which equal to now the expected value, which is equal to ui. That was what's given to us that this moment converges to this particular guy right here. And now by lemma 2 here stated that this moments right here converges to x to the ith power, x to the ith power. Okay. That was lemma 2. So here the function h was here we used lemma 2 with here h of x was x to the ith power. Okay. So we know that this limit, this weak limit, has moments ui. So then by lemma 3, x is uniquely determined by the moments ui. Okay, that was the content of lemma 3. That is this random variable which has all these moments, and that its distribution is uniquely determined. Okay. And by the way, I should have mentioned up here also that we have this when we have tightness, then you have this weak convergence that is from theorem 336 indeed. Okay. So now we have established now that we have a weakly converted subsequence that is converging to X, uniquely determined by the moments. So now let's F be any bounded and continuous function. So then then any subsequence as a further subsequence, say nkl, so that the expected value of f of x nkl converges now to the expected value of f of x. Okay. That is because we know that any subsequence has a subsequence that converges to x, right? That converges weakly to x. So now, so then by the convergence and uniqueness of x, we must have this condition. So we start out with any subsequence, then we must have a further subsequence that converges weakly to a random variable that actually uniquely determined because it has its moments, and then we have this relationship right here. So then by this actually theorem 233 Duret regarding convergence in an topological space, we have that any subsequence here of such real numbers converges to this real number right here. So then by this theorem we have that the full sequence satisfy now the expected value f of xn goes to f of x, the expected value f of x, as n goes to infinity. If this is true, if you have this for any subsequence, then it must be true for the full sequence also. That is the content of this diagram. So here, the topological space is just the real numbers in between 0 and 1, with distance being the infinity norm. Okay, so now we have, but that is nice, because then indeed then we have that xn converges weakly to x. Okay, so this is because this is true for f any bounded and continuous function. We have this relationship, and that is exactly what determines weak convergence. Okay, so that was the proof of the theorem given over 3 lemmas. So now what remains to finish this discussion regarding theorem 3.3.11 is just to prove lemma 3. So the next on the agenda, the proof of lemma 3. So here now we consider, so here so we let x be a random variable with, indeed, as above. I just remind you, ui is the expected value of xi, and here mu of 2k is less or equal to r 2k to the 2k, k being 1, 2, and so forth. Okay, so that is that setting. Then the law of x is uniquely determined. So that is the statement. And now we are proceeding with the proof. So here, let's now phi x say evaluated at t plus h, or we write this as this expected value now of e to the I x times t plus h, right? That is just by definition. And then let me write this now as the expected value of e to the I xt, and then I have this the second factor right here. So let me expand the second factor as the sum I goes from 0 to n minus 1, for instance, and here we have x, h. Let me here use j because we have the imaginary unit up front, so let me use j here. J over j factorial, right? Here this is basic, and then but then here I have a remainder, so let me write this plus plus Rn say of each. So this is yeah, Rn, yes. So I can, let me write it like this. The Rn is the remainder, so that's the random variable, and it's parameterized by the number of terms in the sum and also the offsets here. Okay. So now, if we look at the expected value of the magnitude of Rn h, that is bounded. Here we use a bound for the exponential. When they expand the exponential, that was actually bounded by here, in fact, the magnitude of x h to the n power over n factorial. Okay. So that was a bound that we discussed last lecture. So now, in fact, remember, now we have a bound for this this guys right here. So this for the moments. So this is in fact bounded then by n r h to the n power over n factorial. So here we use the bound for so this was for n even explicitly. We had this explicit form, but you can easily by the monotonic norm you can work out the odd powers also. But you have control of the remainder here from the control of the moments of the random variable. That was the mu i's. Okay, the mu i's. Let me just go back. We had exactly. Now we use this bound. We had the r, and this is n plugged in right there. Okay. And in fact, this is bounded by here we can actually bound this as r e to the nth power. Let's see. I'm missing something. I'm missing h. I'm missing h. H or e. So here, using that, if I look at e to the n, that is the sum j goes from 1 to infinity of j to here n to the j power over j factorial. So indeed, if I evaluate this at j is equal to n, then I get exactly this term right here, n to the n to n factorial. So this term right here is bounded by e to the n. So here I plug in e to the n. Okay. So now we have a bound for the remainder. Okay, we have bound for the remainder. Okay. So any questions at this point? So now the process here is we want to characterize distribution of X, and we know that the characteristic function is a useful tool. We can actually, if we know the characteristic function, then we actually can use the inversion formula to get back to the distribution. So that is the where we are headed. You want to characterize now the characteristic function. Okay. Using the moments. We know all the moments. So now, so then you see that here. So then, but then we know that if H is small enough, this guy right here, when we compute the expected value of this guy, that goes to 0 for H small enough. This guy goes to 0. So then we can conclude. So then for H less than 1 over RE, then this guy is bounded by 1, and we have that we have control of the remainder, so we can actually take n go to infinity. Then we have that phi of t plus h is actually now the expected value of iter I xt, and here I had the sum. I made a mistake. We should start from 0 to infinity. So here it's 0, sorry, 0. And we have x h to the j over j factorial. Okay, with j factorial. Okay. So now this is kind of nice because you have to remember, remember now this was problem 6 in the homework, exercise 3.14 in Duret when we use this. So this is now we're using problem 6, homework 1. This is Duret, I believe, 3.14, when we have this expression right here. This gives us the moments now of them characteristic functions. I can write this as the sum here. I goes from 0 to infinity. And then I realized that I am a little bit sloppy here. I'm a little bit sloppy. Here I should have an I. We have here IXH. So we have, sorry, we have an I right there. So you see that here, when we get down an IX to the J, that corresponding to differentiating J times with respect to T. J times with respect to T. Okay. So now this is the sum of the J derivative of my characteristic function times H to the J over J factorial. So we have all the moments for the random variable, and then we actually have control, or then we have smoothness. We have moment control with the random variable. Then we have smoothness of the characteristic function. Okay, so now that is the situation. So now then this is moreover equal to so here we see that these guys now this is indeed the situation for all T. So this is for t. So then for t is equal to 0, we have that phi OH. So then this guy goes, and I'd only have this guy right here, right? So that's no, this is the sum. J goes from 0 to infinity. I have IH to the J over J factorial, and then I have the J moment. So this is actually new J. And this is for no H in magnitude less than 1 over RE. Thus, indeed, the characteristic function is uniquely determined by the moments for small t. Actually, t less equal to 1 over R. Okay. But then by recursion, the characteristic function or induction the characteristic is uniquely determined by the moments for all t. So here, the picture is the following. So here we have the real line. And then first, let's say we have here minus 1 over RE, 1 over RE, right? And we have that the characteristic function is 1 at the origin. And now we have that it's uniquely determined in this, it's smooth and uniquely determined in this domain, right? Then we can, so this analytic, we have all the derivatives. So now we can actually go here and expand right there. Then we know the moments at this point. So here, know all moments here. So then we can let T1 be this guy right here. And then I can bootstrap myself up to this interval right here. Okay, this interval. And then I can continue like this. So now this allows us to uniquely determine phi. So here, sorry. For t less than, say, 3 half 1 over RE, and then we can continue like this. Okay, so here, this will say 1 over 2 RE, and then I continue like this. Okay, was this process clear? So we can start from the origin, then we have a section here where we know that function is analytic. It uniquely is determined by the moments, and then we can continue piece by piece to the whole real line to have, in fact, that this is beautiful. Now we have the characteristic function. So then, by the inversion lemma, we can find then you can find the law of x from the characteristic function. Indeed, in a unique way. So we have an inversion formula. So then that gives us the law. Okay, that was nice. That is what finished. So that was what finished the proof. So the lemma 3 was really the key result here. So the nice thing, the message is that with a fairly weak growth condition on the moments, it actually determines the law. That's an important insight. Okay. So any questions? Any questions regarding this result now? So that's good. So now let's go on. So next, I will discuss on rate of convergence. And the very this is theorem 349 direct. So this is this result I think is important. So we have the central limit theorem, and we know that if we compute this normalized sum, then distribution this converges to a Gaussian, right? But how fast is this convergence? That's actually that is actually important. So you can see my screen, right? Good. Yeah, because I got some crazy message from Zoom here. But you are still online, so that is good. So so we are connected. That's so now this is what we will discuss next. So leading up to this, so recall. This is essentially problem number 4 in homework 1. So we let's say x be distributed uniformly minus a half to a half, and let's say yn be the sum I goes from 1 to n of xi over square root of n sigma. Okay. And here independently. So now that is the situation. So here sigma squared indeed is not the expected value of x squared, which is 2. Now the integral from 0 to a half x squared dx, right? So here this is actually 2 times 1/3 times 1/8, which is 1/12. So my sigma is indeed 1/2 square root of 3. So that was just a remark. So that is how it's easy. So the key thing is to normalize properly. Okay, that was just a remark. So now this way we normalize. So now so the question is, how fast does the distribution of yn converge to the Gaussian. That is the question. So, or moreover, so in fact here, in this case, yn will have a density. Yn will have a density. Actually, in problem 4, we are explicitly given this density. So, or what can we say about sup in X, or the density of f yn of X minus 1 over square root of 2 pi e to the minus x squared half. Okay. Moreover, sup of over X of the cumulative distribution function of this guy minus the Gaussian. This is the area function, or the cumulative distribution function. This is the area function, the integral of this guy right here. Okay. So that is in fact that is what we will discuss by the Bayesian theorem. So now I will actually, so let me ask you a prompt. How do you think, what will be the rate of convergence here? Any suggestions, any guesses? So so here, you know, it could be fast, not so fast, very fast. What in terms of n, how fast do you expect the convergence to be? Any suggestions? Any suggestions? I don't hear any suggestions. So actually, it's hard to guess. It's hard to guess. But let's look. Let's push this. Let's see if I'm able to. We are almost out of time. So I played a little bit with MATLAB. So let's look at the convergence, since we are almost at lunchtime. So what I will do, I will stop share, and I will show some MATLAB simulations, and then we'll discuss the theory next lecture. So here I'll stop the share. And then I will share again MATLAB figure. So now can you see my MATLAB figure? Okay, great. So now what I will do, I will here. Let's start with n is equal to 2. N is equal to 2. And then I look at the distribution of this normalized sum of two random variables uniformly distributed in between minus a half and a half. So then this actually, what will this look like? So I have a uniform distribution, and I sum these two up. That will have what the distribution will be exactly, will be the triangle. So now we have exactly the triangle. And you see that the dashed red line, that's the Gaussian. So already two random variables, grossly, it doesn't look too far from the Gaussian. It doesn't look too far from the Gaussian. So now if I increase here, so that m be equal to 4, then actually we are getting pretty close. We are getting pretty close. So now, how far do you think you have to go before we cannot see the difference in between the two lines? So here I had only 4 random variables, right? If I push it a little bit further, say I go here to, let me go to m is equal to 30. So that's a small size to undergrad class. So so now if let's say grades are uniformly distributed, then the average is actually very, very close to a Gaussian. So here you see that basically even with just 30 random variables, you are on the Gaussian. So if the grades happen to be uniformly distributed independently, and it's not given that they're independent, but if they are, then the grade distribution, actually average grade distribution, is very, very close to the Gaussian, properly normalized. So that is the standard Gaussian. So one thing to be mentioned here is that one thing that is nice with this function is that we have thin tails. Actually, it's compactly supported, right? Then -half and +1/2. So we have thin tails, actually no tails. And that is something that works in our favor in the central limit theorem. If you have very heavy, what's called heavy tails, so the distribution is very smeared out, then actually we may not even have the second moment. If you don't have the second moment, then we may be in a situation, so non-central limit theorem. We do not have convergence to a Gaussian. But here, with thin tails, we have the second moments, we have rapid convergence to the Gaussian in distribution when we average properly these random variables. Okay. So that we see that it seems that it converges very fast. So ponder this question. So how fast do you think the convergence is? And then we'll characterize this both theoretically and numerically in next lecture. Okay. So thank you for your attention. Have a great afternoon. And I'll see you again on Friday. And as always, feel free to shoot me a mail if you want to have an office hours in Zoom. Okay, take care.